I've shared my screen. Is it visible now?
Yes, sir.
So today it's a second tutorial. We'll discuss few problems. Say one or two problems from net, and then we'll see some more problems from topology which are not in teleprinters, and then we will see the problems which sir has given to you during the classes from the group by teleprinters, like from this exercise mainly. This one. Okay. So we'll begin with the problem from net. So first read the question, like you are given a topological space X and X alpha, and X, it's given that X alpha converges to X. Okay. Now here the index set was I. Now we are taking another index set K and a function K to I. That is, we are taking that is, we are changing the index set in terms of this function G. Okay, and of course this both I and this K are directed sets. Now this index set K has K, if we have alpha less than equal to beta, or alpha is direction beta, this will imply G of alpha is G of beta. And the second condition is, for any alpha belongs to I, there exists some lambda belongs to K such that this alpha less than equal to C alpha. Okay, so this is given. Now you have to prove that the sequence x of g lambda means, if we take this sequence, this net, this is not a sequence, it's a net where lambda belongs to K, this converges to X. So this is the problem. So can you take 5 minutes and try to solve, or if you have any idea? Anyone? Yes. Okay. Solve. So it is given that the net x alpha converges to X. Okay. Now, and we have to prove that X of G alpha, this is also converges to X. So what you have to take? We first take an open set. An open neighborhood or simply neighborhood. X. Now since X alpha converges to X, there will exist for U, there exists some alpha naught belongs to I such that X alpha belongs to U for all or whenever this alpha naught is alpha, right? Now we will move to the second case, like X of G alpha. Okay. Now so you see here you have one element from I, and by this property, by the second property, by this property, for alpha belongs to I, there is k such that alpha less than equal to G lambda. So we have for alpha naught, there exists some say lambda naught, okay, such that alpha naught G lambda naught holds. Now can you see the answer? Can you see how to proceed now? What we have to prove? We have to prove that there exists some say lambda 1 belongs to k such that X of X G lambda belongs to U for all this lambda equal lambda 1. So you have to prove this one. Now you have some lambda naught which satisfies the property that alpha naught is reduction G lambda naught. So now how to proceed?
Sir, we can take here lambda 1 G lambda naught.
Sorry, I can't hear you.
Whereas whenever the alpha naught less or equal to alpha, then X alpha belong to U. Then we have whenever alpha naught less or equal to G lambda naught, then we know that X of G lambda naught belongs to U.
Yes. And
Hence
then
X G lambda is converges to X.
yes, exactly.
Because X is neighborhood of.
Yes. So what actually we for our U we have got this lambda 1. What would be our lambda 1? This lambda naught, right? That's mean now now see if lambda or lambda naught is equal to lambda, what happens then? We have G lambda naught equal G lambda by first property, but in left side we have alpha naught, right? Now we have alpha naught this G lambda for all lambda this lambda naught, but this implies, what does this implies? This implies this X of G lambda belongs to U, right? For all lambda naught, and this implies the convergence. X of G lambda converges to X. Is it clear?
Yes, sir.
Yes. Actually, so I think sir did not define the subnet, right? and he said it is not necessary.
Yes, sir.
Yes, actually this problem follows from subnet, and this is how we define a subnet of a given net. Okay, so this is a remark. Only this is for a remark. Since sir told you we do not need subnet for this course, just say I give a remark that subnets follows from such directed set K. But for the case of subnets, we have to take this K, it has to be a subset of I. Okay. But don't, but since you do not have any criteria for subnets, this is a only remark for you. You do not need this one for your course, and just take this example as an exercise from net. Okay. Do not bother about the subnets and all this. Okay. So now, so is it clear this problem? We will see another problem from net maybe at the end of this class. So yeah, I think it's clear. Let's move to the next problem. So this problem is from your book by Alec Printers. So now it's given that in arbitrary subset, so X is a Hausdorff topological space. It's given that X is Hausdorff, and we have to prove that the derived set, this is called derived set of any the derived set of A, where A is subset of X. So first of all, what is the definition of derived set? This is the collection of all
limit one.
Yes, collection of all limit points. So can you see that the derived set is closed?
Yes, sir.
How?
So for every convergent sequence,
Then
so for every convergent sequence, the limit will lie in the derived set.
yes, then
Then the derived set will close.
you have to consider this one, right? The Hausdorff property will come to that point, right? Yes, it is fine that every convergent sequence will be lie in the derived set, and then okay. So actually, okay, let's see the problem in a little different way. So, what is the definition of a closed set? A is closed, or say some set B, closed in X if B complement is open, right? This is the first definition of closed set. Now, here what we prove that the derived set of a complementary derived set is open provided X is Hausdorff. This Hausdorffness is very important, okay? So this one is very important to give the derived set is closed. Okay. So this is simple, right? So let an element X from its complement. And what does it implies? It implies X does not belongs to A dash. Yes. And what does it follows? There exists
set.
Yes, there exists an open set.
So that U intersection A minus X is empty.
Yes, U and then
Intersection A minus X
yes, exactly. Intersection A minus X
is empty.
is empty. And then so this can be taken as U minus X intersection A, right? These two are same. Anyway, so from here, what our claim is that this U subset of A dash and its complement. Okay, so to prove this one, we take, so is it clear that if we are able to prove that this U is contained in A dash complement, then U will be a neighborhood of X such that X belongs to U and. Okay, so this is very important. So this U will be a neighborhood of X which contained in A dash complement, and therefore this will be open. Now our claim is to prove, or aim is to prove this U is contained in here. So take an element Y from U. Okay. Now you see X is already in A complement, right? Now let us take some different element which is not X, like take some element Y from U where Y not equal to X. Okay, so then what we can say by Hausdorff-Nash?
There exist
Then
neighborhoods.
there is a two open set.
Yes,
So
there
that BX
exists.
intersection BY.
Yes, yes.
The
There is
intersection
two
is
open set,
UX, UY,
and so that UX intersection UY is empty.
UX intersection UY is empty. Okay. Also here, make sure that you say UX and UY containing X and Y respectively. Okay. Just give the complete statement. This is empty. Right? Now you take this UY intersection U. UI is an open set and U is an open set, right? UI is an open set and U is an open set, right?
yes, sir.
Yes. So therefore, their intersection is open.
Yes.
This intersection does not contain X. Now, if we take
Yes, sir.
UY intersection U intersection of A minus X. Y belongs to this and this is an, or this is a neighborhood of Y, you can say. Right? So this intersection, that what it is? It is a subset of U intersection A minus X, but this is empty. So what we can say is that this is a neighborhood of Y, right?
सर तो यहाँ से भी तो कह सकते हैं ना कि सर वहाँ UI इंटरसेक्शन U में सर X बिलोंग करेगा नहीं.
UI intersection, sorry again, फिर से बोलो.
सर UI इंटरसेक्शन U में सर X कभी बिलोंग नहीं करेगा.
हाँ, X
और
कभी belong नहीं करेगा.
A माइनस X में भी X बिलोंग नहीं करेगा.
हाँ,
तो यहाँ से भी इसका
ऐसे ही
इंटरसेक्शन
बोल
नहीं हो तो
सकते,
एम्प्टी आ
ऐसे ही
जाएगा.
बोल सकते, कोई दिक्कत नहीं, ऐसे ही बोल सकते, कोई प्रॉब्लम नहीं. ठीक है. So, and this implies y does not belongs to a derived set, right? Is it clear? इसको हम सेम बोल सकते हैं कि u y intersection u intersection a, right? Because x is not here, because x does not belongs to the first set. So इसमें से क्या बोल सकते हैं? This is a neighborhood say V. So there exists a neighborhood V of y such that V intersection A is empty. Okay. तो इसमें से क्या बोल सकते हो? This implies V does not belongs to, sorry, not V, this is Y does not belongs to a derived set. Right? Is it clear? And this implies U subset of this one. Y was in U, now Y is in, means Y belongs to a derived set complement. So U subset of a derived set complement. So this implies a derived set is closed. Okay. So it will be more clear if I give you an example where the space is not housed off. Okay, so now let's see some example where the space is not housed off. So I can't get this space here.
Sir, in discrete topology.
In
discrete topology where x equal to a comma b.
Yes, then
From here, sir, a dash is not closed. Suppose a equal to singleton a.
Then
So that was not housed off, so it is counterexample.
saying which topology in discrete, right? This one empty set comma x.
Yes, sir.
Right?
In discrete
Yes.
topology.
In discrete or discrete?
Sir, in discrete.
In discrete. This one, right? This one only.
Yes.
Yes. So now if you take any set A, then
Sir, x. Sir, in
then
discrete topology,
a non-empty set. Yes, it is not housed off. Then
and sir, x take a comma b. X take a comma b.
take x equal to a comma b. Okay.
And a singleton a.
Or a as singleton a. Then
Now find a dash.
now what is a dash?
A singleton b.
Singleton b. Yes.
And we know that here is only means here it is not closed.
Here it is not closed. Yes, it is not closed. Exactly. Exactly. Thank you. A simple example that housed property is necessary, right? For this case, I'm giving you another example. Just this is for an exercise for you. Take x to be R, and the topology tau define the topology tau by the basis. The topology tau by which is generated by the set basis where B is a comma infinity. A belongs to R. Now try to see this. Now take the set, say minus infinity comma 0, and try to find out its derived set and compare with this example. Okay, this is an exercise for you now. Will I bring this one to give a counter example, but yes, I can. So this is an exercise. Not now, so compute this one and you will find it by yourself. Okay. Try to solve this problem. Now we will move to problem number 6. Now tell me whether it's clear to you. So if it is not clear, then ask me, I will explain again. Yes, anyone? Okay, if not, we will move to the next problem. Now take this as an open cover topological space X, means your X is union over index over, say here I forgot to write the index, I belongs to the index set I. Okay, I is OIs. Okay, now say a subset of X is open. Okay, now tell me what is relative topology? This is actually the subspace topology. Okay, means subspace topology. I hope you know the definition, right? Yes. Do you know the definition of this one, subspace topology?
Yes, sir.
Yes,
Yes,
sir.
yes. And the relative topology is same. This two and this term are same. Okay. So now we take A, an open subset in X. Oh, got to put the closeness. The reverse one. Right. So it's closed. You have to prove that A intersection with this one is open, sorry, is closed in this side. So this one will be closed in now see A open in X, sorry, A is closed in X. This will imply A complement is open in X, and this implies A complement intersection OI is open in where?
OI.
Yes, OI. Right? So and therefore its complement, this OI minus A complement intersection OI is closed in OI. What is this one? This is same as OI intersection A complement, right? Oh, sorry, this is not complement. This is A. OI intersection A is closed in OI. Okay, this one is simple. Now let's move to the previous, the converse one. Reverse one. So now let A intersection OI be closed for each I. Okay, so this one is closed in, here I have to say in this OI for each I. So what does it imply? This implies OI minus OI intersection A is open. Now if we take, so this is open in OI. Now let us take it as UI. Okay, now OI is open in X and UI is open in OI. So what can we say about, can we say that UI is open in X? Can we say this one? See, UI is open in OI. So what does it mean? It means that UI equal to, so what are the open sets in subspace topology? This ui is equal to,
Sir, A intersection OI where A is open in.
yes, A intersection OI where A is open in X, right? Now see, UI is the intersection of two open sets A and OI, and both of them are open in X. So can we say that UI is open in X?
Yes, sir.
Yes, so UI is open in X. So answer is yes. Now UI is open in X.
Sir, OI is open or closed? I'm confused.
OI are open cover, right? They are open.
Okay, sir.
Yes. UI is open set. Okay. So this one. Now you see, now what we have to prove is that we have to prove A is closed in X. So we have to prove. That is to prove that A complement is open. Now what is A complement? A complement is equal to X minus A. So what is your X again? Because OI is an open cover.
Union of OI.
Yes. So this is union of I belongs to this side OI and this minus A. So can we say that this one is union of I belongs to I, this OI minus A?
Yes, sir.
Yes.
Yes, sir.
Yes. Now, what is this? OI minus A?
Open.
Yes, this is open. Open in OI, right? And therefore, this one is open in X. Is it clear? See, A was closed in OI. So this implies OI minus A is open in OI. Now this one is open in OI and OI is open in X implies this one is open in X, right? And this one is open in X and this is the arbitrary union open set. So therefore this one is open in X. So what we can say is that this guy is open in X. So what is this one? This is nothing but A complement. So A complement is open in X. And so A is closed. A is closed in X. Okay. So is it clear? If yes, I will move to the next problem.
Sir,
Yes?
sir, please repeat the converse part.
Sure. So, okay. So, what is the converse part? We have to prove that if for each if A is closed, what to prove for the converse? If A is closed in each OI, then this will imply A is closed in X. So you have to prove this one. Okay. So now for the so now let this one is closed. Oh, sorry, not this one. It's A intersection OI. Okay. So now let this one is closed in OI. So what does it mean? So this one is closed in OI means with respect to the subspace topology. Right. Now if we take the complement of this one in OI, so what it is? It is if we take it as UI will be OI minus this one. This one is a closed set in OI, and so this is an open set in OI. Right. Now I claim that if OI is open in if O, so let me give a general statement. Means if V is open in X, and if U is open in V, and here the topology is a subspace topology, then what is this U? This U is a subset of X. Then this subset will again form an open set in X, means an open set with respect to the topology of X. Then U is open in X. I have proved this one only by this statement. Okay, so is it clear that when this is open in X and I have taken an open subset of Y, now UI is open in Y and OY is open in X, this together implies UI is open in X. Is it clear to you?
Yes, sir.
Yes. So now we will use this one, this fact only. So now we have to prove that A is closed in X. So that means we have to prove that A complement is open in X. Now what is A complement? A complement you can write down as X minus A. But your X was this union, and this union, this minus and A. So A complement is this union minus A. Now this can be written as this one. So union of I belongs to I, OI minus A. Now each of these terms are open in Y, right? And Y is open in X. Therefore, each of these terms by this result, each of these terms are open in X. And so this is the A complement is the union of open sets, and therefore it is open. And so A is closed. Is it clear now?
Yes, sir. Clear.
Yes. Okay, so whenever you have doubts something and some if somewhere you are confused, then you should ask me. Okay, I am here for you people only to clear your doubts. Okay, so now the next problem. So this one is the easiest problem, I guess, between 1 to 11. That problems has given during the classes. So let me give some hints. Number 1, if B is subset of X, then B interior is open in X. Do you know this one?
Yes, sir.
Everyone knows it? If there is someone
Yes,
who don't
sir.
know, please tell me. I will prove it. Right? And the second one is, okay, not this one is 1, and second one is B naught is the largest open set. Open set where?
Contained in B.
Yes, contained in B. So we will use this fact only. Okay. So now let F is continuous. Let F be continuous. Let be continuous. Okay. Then what we know is that B is any subset of X, then B naught is open. Sorry, this B should be a subset of Y. Open in Y, and continuous implies, what does it implies?
Inverse of
F inverse of B
Not is
naught.
F inverse of B naught is open in where?
X.
Open in X. Yes, you should write the complete statement. Okay. So always, whenever in the paper or somewhere, whenever you are writing some mathematical argument, you should write the complete one. So now again, this B naught is contained in B, so we can say F inverse of B naught is contained in F inverse of B. So F inverse B naught is an open set contained in F inverse B, but F inverse of B, this knot is the largest open set. So what can we say from here? This is the largest open set contained in F inverse B, and therefore we can say F inverse of B naught subset of F inverse B and its interior. Okay. Can we prove the converse part? Converse part is very easy. Okay, just so it is given then F inverse of B naught subset of F inverse of B naught. Okay, so what you have to take is that you have to prove F is continuous. Can you prove it? Can you prove this one? Okay, let me give you this one as exercise. No, it has already given to you as an exercise. So let B subset of X, not B subset of X. Now let U be open in Y. So once when U is open in Y, this will imply U not equal to U, right? U is same as its interior. Now by this result, F inverse of U not subset of F inverse of U and not, but this is same as F inverse of U is contained in F inverse of U not. So what can we conclude from here? What is the conclusion?
F inverse U equal to F inverse.
Yes, F inverse U is equal to F inverse of U naught. So this one is open. Okay. So let's quickly move to the problem number 17. So every closed subset in a metric space is a Z delta set and every open set is a F sigma set. So do you know what? Can I prove this one? Or you know how to prove? Yes. Note that here the metric space is given. Shall I prove? Okay, let's prove. What we need actually need problem number 7. Yes. Actually, this is construction type. So what is G delta set? Countable.
Intersection of open
Countable. Union or
Intersection.
Intersection. Yes. Intersection of
Open set.
intersection of open sets. Okay. So the next one is, so you have to prove that. So okay. So let A be a closed subset. X be a closed subset. And we are taking the metric space as X comma D. Okay. Now, do you know the function f from X to R, or more precisely X comma D to R comma this one, defined by fx equal to D of X comma A is continuous? Do you know this one?
Yes, sir.
Yes, we just need this fact only. Okay, so once this one is continuous, then inverse image of closed set is closed. We know this one. Further, when we are given that A is a closed set, we can precisely write this F inverse of 0 as this will be precisely F inverse. Your S, the set A will be F inverse of 0. Okay, where A is closed. Now, F inverse of 0, how do you define F inverse 0? This is same as F inverse of intersection of open sets. So, this will be n belongs to say n 1 by minus 2 to the power n, comma 1 by 2 to the power n, right? And this is same as intersection n belongs to n F inverse minus 1 by 2 to the power n, comma 1 by 2 to the power n, right? So each of these terms are open, and so your A is countable intersection of open sets, and therefore A is exit data set. Right? Is it clear? Only this portion, right? How A becomes F inverse 0 singleton set? Actually, I am assuming here, no, not assuming, there are some standard result in metric space. This is result from metric space. I am not going to prove here. You can find metric space result. Okay. So yeah. So what is?
सर एक को सर क्लोज जो है लेट करके चलना पड़ेगा पहले.
हाँ बोलो.
सर एक को सर क्लोज लेना पड़ेगा तब होगा ये ट्रू. ओके सर.
एक क्लोजर पे क्लोज लेना पड़ेगा. क्या बोल रहे हो?
सर हो गया क्लियर. सर मैं बोल रहा था कि एक को सर क्लोज लेना पड़ेगा बट आपने पहले लिख दिया था कि एज क्लोज.
हाँ हाँ एक को क्लोज लेना पड़ेगा. हाँ हाँ. And the second term was, the second part was every open set is an F sigma set. Now you see this is a result from your the book by Elephanters that if a set is G delta set, if and only if its complement is a F sigma set, right? Now just use that result only. Okay, there is a the second part by result in the book, or let me tell, A is a G delta set if and only if A complement is a F sigma set. Okay, this one. We move to the next problem. So actually this one has defined by taking first has taken it as a basis, and sir told that tau means this collection will form a topology, right? So have you verified this one? It was done in the class on Saturday. So sir told you to verify. So can you do that? Yes, no? Tell me whether I have to,
we will try.
tell me whether I have to try now. Means shall I solve it now, or I can leave it for you?
You can leave.
Okay. Okay, sir. Okay, so I'm leaving it for you. It's an exercise. Please try to solve. Okay. Once you see this one, then you will understand how the basis gives you a topology. So please try to prove this one. Okay. I am writing this VVI not for exam, for understand the topological spaces and basis. Right, to understand topological spaces and basis. Okay, everyone, please try to solve this problem or please try to prove this one. Your tau is a topology. Okay. Okay, so I'm for the moment I'm leaving it for you. Okay. So the next one, this one again this problem was an exercise for you. The certain field line or the topology, the lower limit topology in RL is separable. So can you see this one? RL is separable. So RL is separable. How? Quickly.
Q is dense, sir.
So your claim is Q is dense in RL. In R with respect to, or let me write it as horizontal plane, or let me write it as simply RL. Okay, so how?
Sir,
Means
for any x in R
for any x,
in
what
R,
will be the neighborhood?
x to x close comma x plus R is greater than 0.
Okay, try to write the closest as x minus epsilon comma some x plus delta. Okay, let's write in this way where epsilon not in this. Actually, I'm trying to cover all the open sets. So x minus epsilon to cover epsilon can be 0 or negative. Anyway, okay. Now, if you take any open set of the or any basic open set of this type, okay, which if this contains x, then this one will also contain a rational number, right? How?
Yes.
How? Because this is by the density property of Q in real life, not in RL, in real life, right? Like if between any two rational number, between any two rational number there is irrational, and between any two irrational there is rational, between any two real number there is rational by this result. Okay, so this Q is dense in RL, so therefore certain field line is separable. Now what about the second countability? Is this second countable? Okay, let me prove this one. So to prove second countable, what is the definition?
Countable base.
Means countable basis, right?
Context.
Yes. So okay, let's see. Now let us first take this B be a basis for RL. You have to prove that B has uncountably many elements. Okay. So now take X belongs to R. Okay. Then and consider the neighborhood like X comma X plus 1. This is an open set in RL containing X, right? Open and contains X. So then what can you say for this open set in terms of basis? there exists a bx or bx belongs to the script b such that x belongs to bx which contained in x comma x plus 1, right? Now choose an element y which is not x. Okay, I'm taking another element which is not x, and so what can we say then? We can say either x less than y or y less than x, right? So which are okay, so and suppose x less than y, the similar cases will happen when y less than x. Okay, if x less than y and if we consider y comma y plus 1, then similarly we will have one such by, right? We will have one bx and we will have one by. So what can we say about the relations b1, bx and by? These two are not same, right? Bx not equal to by, right? Can you see this? That bx and by are not same?
Yes, sir.
Yes, because x
Y is greater than.
does not belongs to by, right? X is less than y and by subset of y comma y plus 1. So x is not in by, and therefore simply we can say bx and by are different, right? And thus, so thus for each, and see I did it for x less than y. The similar thing will happen for y less than x also. Okay, in this case also you will find some by, and this by in this by, and in this case y will not be in bx, and so bx not equal to by. Okay, see I did not verify the term that whether by contained in bx or bx contained in by. Okay, I didn't verify this one, but I have taken the intervals of length 1. So definitely if this is a real line, if your x is, if this is of length 1, and if you take another set from here, you will definitely, okay, let me state it precisely that bx and by are not same. Okay, so it can happen that at the moment we have bx is not by. Tell me one thing, is it fine if we say one is not contained in the other, then these two sets are different? Yes, you can see, right? So bx, if one of them, if there is something is the complement of in real complement, then this set cannot be same. Anyway, yes. So this one is true. Now, thus for each x belongs to R, we have a bx, right? And this bx belongs to the script b, right? So what can you say about the cardinality of this b, the basis? This b
Greater than equal to cardinality
that,
of R.
yes, greater than equal to the cardinality of R. So therefore b is uncountable, right? So I have taken an arbitrary basis and proved that it is uncountable. So this RL is not second countable. Okay. So I have two more problems. So shall I continue for 10 more minutes? Or you have
Hello,
something else? Huh?
सर आपने जो y चूज किया है ये सर किस सेट में बिलोंग कर रहा है? x
कौन
x
सा?
plus 1 में सर y
Yes, this Y.
सर y belongs from where? Is x x plus 1?
No, I have taken arbitrarily. See, it can be in here, it cannot be in here. We don't know. Okay. So it can be from outside, it can be from inside, we don't know. Just simply the one point which is different from x. Okay. Yes, I can also see there is a confusion. Like one may contain the other, and in this case we can refine, but we cannot. Means, well, ultimately you will see that this bx and by are different, and this will produce this script b as an uncountable set. Okay. Like if you consider that this bx, then this bx will not cover all the elements of by. Means ultimately if you say u belongs to say bx, and if you want to cover see, actually when we can reduce the number of elements in the basis, like whenever two sets we get some bx and by, and one of them are contained in the other, and we remove and replace these two set by one single one. Okay. But in this case, means for RL, you cannot do such things. Just think about it. You will find your answer. Okay. So can I continue for 10 more minutes? Oh, it is already 4:18. Okay. Let me just give you some hints. So do you know the product topology? No, right?
No, sir.
No. Okay. Then we okay. Then we will solve it after you learn product topology. Okay, then leave this one, and the final one. This RL and RK are not comparable. Okay, so you have a single set X and define two topology tau 1 and tau 2. So suppose tau 1 contained in tau 2. So then what we can say here means what are the names? Since tau 2 is finer than tau 1, right? Finer or stronger, right? Then tau 1, and we say tau 1 is weaker than tau 2. See here, RK and RL both are topological spaces, means both are giving topologies on the same set R, right? And what do we mean by comparability of two topological spaces? Either comparable means either tau 1 is weaker than tau 2 or tau 2 is weaker than tau 1. Okay, so either this or this one, then we say this space, the two topologies are comparable. And here we are saying that not comparable, then so that's why we have to prove that RL is not comparable to RK, is not weaker than RK, and as well as RK is not weaker than RL. That is, you have to find out there exists open set in RL which is not open in Rk. Okay, and by this we mean there exists open set in Rk which is not open in RL. Okay, so means you have to prove that these two topologies are not comparable. So means you have to find out an open set in RL which is not open in Rk, and an open set in Rk which is not open in RL, right? So is it clear, the definition?
Yes, sir.
Yes. So now let's recall first what are RL and R. So you know the RL, right? The certain field line. Now let's look at the definition of Rk. Rk is the topology generated by the elements, this kind of open intervals, and this kind of sets minus k, where k is this set. Okay. Rk is generated by this basis, and you will understand the topology whenever you prove this theorem, or sorry, whenever you prove this result. Okay, whenever you prove this result, and only then you will understand the topology. Okay. Before that, let me prove. See, 2,3 is open in RL, right? 2,3 is open in RL.
Yes, sir.
Yes, sir.
Now,
Yes, sir.
whether is it open in Rk?
No, sir.
Why?
Sir, it is not the form of A, comma B.
It is form of yes, you are right. It is not open in Rk. Why it is not open? If you take the point 2, right, then what kind of neighborhoods of and consider neighborhood 2 minus epsilon comma 2 plus epsilon. This kind of neighborhood of 2 in Rk, right? In Rk, the neighborhoods of 2 will looks like this one, right? So 2 minus epsilon comma 2 plus epsilon, right? Because this kind of because if you consider an open set U minus k, then k is not here for this set U, right? If you take U as this one, and if you take k as 1 by n, then this will not change. This U minus k will same as U. That's why if you take an open neighborhood, it will look like this one. Actually, of course, those are basic open sets, you can say. So this kind of open sets, this will be a neighborhood 2 in Rk, but this 1, 2 minus epsilon comma 2 plus epsilon is not contained in 2 comma 3. Okay, and so this one is not open in Rk. And again, when I am giving the solution of proof of this one, I also understand that this will not clear to many of you, but this will be cleared once you solve this problem. Okay, to first solve this one, that this tau forms a topology, this tau forms a topology, then you will understand what are the open sets in Rk looks like, and then you will understand that sometimes instead of taking open sets, if we are able to, if we can, sorry, sometimes instead of taking open sets, if we are able to deal with the basic open sets, then this will be fine. Means the dealing with basic open sets will be enough for us. That's what I did here, and then you will understand this one. So now for the moment, I am saying that 2, 3 is an open set in RL, but this will not be open set in RK. Okay, and given an ultimate idea, sorry, given a rough idea, so you will understand once you prove this kind of topological means if we once we are able to see the topology on RK. Okay, so if it is not, please tell me in the next tutorial session. I will explain it once again. Okay, so now look at this one. So why RK is not comparable? So why RK is not contained in RL? See, minus 1 comma 1 minus K is open in RK, right? Is it open?
Yes,
Yes,
sir.
sir.
By this kind of basic open sets. Yes. So now this is open in RK, and also this contains 0, right? 0 belongs to here. Now, what are the neighborhoods of 0 in RL? They must look like A, comma B, right? Or in other words, yes, I have to take any arbitrary one, taking 0 and A will be a particular case. Okay, so A or 0 minus epsilon, comma, say some B. This will be the open set or neighborhood of 0 in RL. Okay. In other words, is minus epsilon, comma B. Right? So, can we say that this one contained in minus 1, comma 1 minus K? Is it
No,
true?
sir.
Why?
No, sir.
Why?
Sir, we remove K from.
Yes.
But in the interval minus epsilon to B, there is element of from K, sir.
Of the form?
All from 1 by n.
Yes, of the form 1 by n.
Yes, sir.
Means there exist elements in minus epsilon comma b of the form 1 by n, right?
1 by n.
Why?
Yes.
By which property?
By Archimedes.
Archimedean property.
Archimedean property. Archimedean property of real number, right? Yes.
Yes,
And that
sir.
is why we cannot say this is not contained in 0 comma sorry minus 1 comma 1 minus k, and so this set minus 1 comma 1 minus k is not open in where to write. Okay. So minus 1 comma 1 minus k is not open in R
Ed.
R
RL.
L. Yes, L.
RL, sir.
This is here 5. That's it. So we can say that these two topologies are not comparable. Okay. Tell me if you have any question, or we will solve this one. Say, mhm. Okay, tell me if you
Hello,
have any
sir.
doubts.
Hello, sir.
Yes.
Sir, I have one question that is
Tell.
from metric space.
Yes.
Sir, suppose two metric space is given, sir, and said that there is a one continuous.
Okay. So x comma suppose two metric space given x and
Yes.
y.
Yes, sir.
Yes.
And
Then?
sir, one continuous map is given.
One continuous map is given.
Yes, sir.
Then?
Sir, my question is that if suppose there is a Cauchy sequence in x comma d1, then fxn is
Cauchy in x comma d1, yes.
then sir fxn is also going to be Cauchy or not in x y comma d2.
Fxn is Cauchy or not.
Sir, I guess not.
Sir,
Because
no.
take
Sir.
xn equal to 1 by n and x take 0, 1 open. Then it is Cauchy in 1.
Xn equal to 1 by n and take
Fx equal to 1 by x.
Fx equal to 1 by x. And your y will be 0, 1 open, right?
Yes, sir.
You cannot take 0. And then your xn is Cauchy. Fxn is n, right?
Yes,
Sorry.
sir.
Fxn is n, right? And so it is not Cauchy.
Yes, sir.
1 second, we cannot take 0 y as it is x, right? So x should be 0, y. Fine. So continuous image in the Cauchy sequence need to be Cauchy.
Sir,
Yes.
and suppose sir means if the sequence is going to be convergent, then it is also implied that the another sequence is also going to be convergent.
Actually, this comes that whenever your sequence xn converges to x, I think in this case you need y to be a complete metric space.
Yes, sir.
Yes. Let me think.
So by sequential approximation of continuity, from where xn is convergent if and only f is continuous if and only if for every xn convergent in x, fxn is convergent in y.
Yes. And in this case, it has to be convergent, right?
Yes, sir. Yes, sir. Convergent is mapping. Means xn convergent, then fxn
Means
is
we need the convergence. Actually, here the Hausdorffness are coming, right? And this one first countability kind of things. Continuous, if and only sequence are continuous.
Yes, sir. Yes, sir.
Yes. And by this one you need, yes. In this case, if it is convergent, then it will be convergent. I'll also think about it and let you know the complete answer.
Okay, sir. Thank you, sir.
Yes. So any other problem?